Thank you for all being here. My name is Max Hinson, and I've been working with Joey Durham in Professor Bulow's robotics lab this summer. And I've been working on programming a 3D simulator for a robotic arm using the RRT motion planning algorithm. So autonomous robotic arms have been around for a couple decades now. They started off in assembly lines for manufacturing automakers, sort of very industrial purposes. And just in the last decade or so, very recently, we've started to use them for different applications like space shuttle maintenance, military vehicle servicing, and not a robotic arm, but an autonomous robot that you may have heard of is called the Roomba. You just set it down in your house and you let it go vacuum your house for you, and you don't need to supervise it at all. So what we're doing with our research is we're working with algorithms so that we can tell the robots what we want them to do and let them figure out the rest. So my project goals specifically were to use the Rapidly Exploring Random Tree, or RRT, algorithm and combine it with a user, an interactive simulator for a robotic arm so that the user can manually place obstacles and goals and tell the robot what they want it to do, and then let the motion planning do the rest. So the first step in working with motion planning is creating a distinction between the workspace and the configuration space. So in the workspace, as you can see here, we've got our 3 links, and our arm has 3 degrees of freedom, one for each link, and they can all move at angles between -pi and pi. They can rotate around freely. So once we sort of recognize that, then we can say, well, any position of the arm can be represented with 3 variables, 3 angles. So what we can do then is sort of create a configuration space. And this configuration space for this project has 3 dimensions, one for each degree of freedom. And so each orientation, 3 angles, can be represented by one single point in the configuration space. So what this allows us to do is sort of start with a complex setup and then make it more simple, sort of slimming it down into one single point. So just so that maybe you can visualize it a little better, here are a couple different scenarios of 3 angles and one point that represents it. Here's a different orientation, and there's a different point that represents that one, and a third one with a different point. So the RRT algorithm is one of a few motion planning algorithms that are sort of making the rounds right now. And it's very popular because it is very, very simple, and it works in almost any case, in even very complex environments. So the premise of the RRT algorithm is that if you have a starting point orientation and you have an ending point, then you're just going to sample and pick random points in your configuration space and create lines that go towards that random point. And so you'll be expanding your tree in random directions until you reach the goal. So here's sort of an overview of how the motion planning works. We've got our initial setup. In this case, all the angles are set to 0. And you can see here the point 0, 0, 0 in our configuration space. And we've got this point that we want to go to. So once we know our start and our end points, then it's just as simple as expanding the tree in random directions. So the tree will expand randomly, and then once the tree gets to within a certain distance, a very small distance, of our goal here, then basically it will pick that leaf of the tree, and then it will backtrack towards the beginning. And then it saves all the points between the start and the end. And that list of points is called our path. So once we've got our tree expanded out and we've got our list of points in the path, then all that's left to do, the hard work is already done, so all that's left to do is is telling the arm, okay, well, here's a list of points that I want you to go through. Now, go do them. And as you saw in that video, it was very quick. Once the RRT algorithm, the motion planning goes first, and then the arm can move through those points. So that method works great as long as you don't have any obstacles that you're going to need the arm to avoid. So once you introduce some obstacles, then you're going to need to be a bit more careful about which points you add to your tree. So before we would just pick random points and blindly add them to the tree, but when we've got obstacles, we're going to need some sort of collision detection. So how it works here is before it adds a new point to the tree, it's going to check and say, at these 3 angles, what will that do to the arm? Will that cause the arm to look like something like this? In which case, that arm will collide with this box. And it's safe to say that that's not a point that you're going to want the arm to use. So if that happens, then we can safely assume we don't want that point, and it's denoted by a little red circle. And so if you throw that point out, then you can just continue with the algorithm as usual until you expand the tree when it hits the goal position. So because the RRT is a random algorithm, you're expanding your tree in random directions, there's going to be some sort of suboptimal path that you're going to calculate. As you can see here, these 5 green points, say that's a path that the RRT has chosen for us. Now, this might be, odds are, it's probably not the most efficient path that you could take to the goal. So what we want to introduce is some sort of path smoothing algorithm. And what we do here is we go through the path every other point, and we average these 2 points together and say, well, what if this middle point just happened to be here instead? Would that cause any sort of collision with obstacles? And if it doesn't, then we can safely remove that point. So we made the path a little bit more efficient there. And so we can continue this path smoothing recursively until we're able to smooth the path down to maybe only 2 points, as long as that path smoothing does not cause the arm to collide with any obstacles. And so here's an actual screenshot of the RRT and its path smoothing. So the green line here is the original path that it calculated. And as you can see, it's real jagged. If the arm was to follow that path, it would be going through a lot of unnecessary motion and very inefficient. So after the path smoothing algorithm, we've got the red line here. As you can see, it's only 1, 2, 3, 4 points in that path, as opposed to maybe 20, 25 for the green one. And so as you can see, the red line did not go absolutely straight from the start to the end, because there were certain obstacle points that would cause collisions. So the path smoothing is very important in optimizing the arm's path. So in summary, this simulator will be used as a teaching tool, hopefully to help students better understand how the RRT algorithm works. Here's a screenshot. On the right here, this panel shows the RRT working. Unfortunately, I could not get a video of the RRT expanding while the simulator was running, but I could get the arm actually moving. And so as you can see here, the arm's motions are very deliberate. It's not making a whole lot of unnecessary movement because the path smoothing algorithm has already been done. So in closing, I would like to thank Matt and EUREKA, as well as the EUREKA program for the opportunity, and especially Joey Durham and Professor Bulow for all their help and support. And thank you guys all for showing up today. So are there any questions